Yeah. So let me clarify. Yeah, but yes, he visited my laboratory. So
Sir,
that's yeah.
thank you. Good morning to one and all. It is our pleasure today in the second day in first session. Today we will have one of the eminent personality, Professor Pradeep Dikshit. He will deliver the talk on glass micromachining by electrochemical discharge machining. Uh, Professor Pradeep Dikshit is now working as an associate professor in Department of Mechanical Engineering, IIT Bombay. He has earned his PhD degree from NTU, Singapore in year 2008. He did his postdoctoral fellowship in Packaging Research Center, Georgia Tech, with Professor Rao Tumal. Before IIT Bombay, Dr. Pradeep was a senior research in VTT Technical Research Center of Finland, where he developed 3D packaging technology for MEMS sensor. Dr. Pradeep is also an associate editor of Microsystem Technology. So far, he has published more than 50 articles in peer-reviewed journal. He received Norman Hackerman Young Award, Author Award in 2006 for his work on aspect ratio dependent copper filling process. His research interests are in micromachining, MEMS fabrication, and 3D packing. Now I request uh, Professor Pradeep Dikshit to present the session.
Okay. So thank you, Dr. Dev. I hope that I'm audible. Okay.
Sir,
So I'm going to share my screen. Please let me know if you are able to watch this. And I'm going to stop my video just to save the bandwidth for all the participants. Okay.
sir.
Great. Please let me know if you are able to see my screen, which is yeah. Okay.
Yes, sir.
Yeah. Okay. Very nice.
Sir,
Right. Okay. Right. So thank you again, Dr. Dev. So currently I'm working in Department of Mechanical Engineering at IIT Bombay, where I am mainly trying to explore different low-cost micro machining technology, mainly for brittle materials. Okay. So today I'm going to talk about glass micro machining, which has a wide number of applications, not only in the conventional field but more in the field of sensors. Okay. However, this technique, which I'm going to talk about, electrochemical discharge machining, it is also applicable for other brittle materials, other ceramic materials, non-conductive materials like alumina, silicon carbide, okay, and of course with glass-based materials. Okay. So here are my contact details. So those who have any questions, okay, you can basically contact me through email, or you can also call me, not a problem. Okay. So my outline in next 1.5 hour, I'm going to talk about mainly about the glass, okay, which is nothing but a silica based material. And I'm going to talk about that why we are having so much interest in glass now. Okay, so everybody is familiar with glass. We are using in our kitchen applications, window pans applications, automobiles also. Okay, but because of this display technology, right? So especially for mobile phone, tablets, computer, we are seeing more and more growing interest in the field of glass. Okay, so I will talk about the growing application of glass as a substrate material. Okay, then I will give you kind of a glimpse of the different micro machining technology which can be used in principle for glass based materials. Okay, so I'm assuming that most of the participants are from mechanical engineering, and as a mechanical engineering engineers, we are familiar with the technology like abrasive jet machining or ultrasonic machining or laser ablation process. Okay, so mainly we will discuss about electrochemical discharge machining, okay, which is a hybrid machining process. So this process is not very new, okay, it has been going on from last 10 12 years, okay, but in last I would say 5 years, we are seeing more and more interest in this area. Okay, so I will talk about the basic fundamentals of process mechanism. Okay, what are the important parameters? Okay, I will talk about the main research activity which is happening in my research group at IIT Bombay. Okay, um, once we cover these fundamentals, then we will show you how this particular technology can be used to create something called as a through glass via, which is also known as a 3D interconnects. Okay, 3D interconnects, and these 3D interconnects are present in most of the mobile phones. Okay, so most of the mobile phones which we are using right now, they are using some kind of a 3D interconnects, but those are slightly different from glass. So they are basically known as a through silicon via. So instead of glass, tech companies like Sony, Samsung, they are using silicon as a substrate. Okay, and I will indicate that why glass is becoming more important now. And then I will show you one of the application, one of the low cost fabrication of 3D components, which is going to be utilized in MEMS application. So MEMS stand for micro electromechanical systems. It is mainly about those small miniaturized sensors which we are talking about. Okay, and at last I will conclude my outline. So if you have any questions, I would request all the participants that please do not hesitate, because the main objective of this faculty development program or FDP program here is to basically share the research activity which is happening all over the country. Okay, so if you have any questions, or if you feel that this technology can be used for some of other applications, please feel free to contact me. Okay, ask a lot of questions so that we can have an interactive section today. Okay, so now let's see. So as I mentioned that most of us are already familiar with glass. Okay, we are using this glass for so many centuries. Okay, so glass is nothing but a silica based material. Okay, so silica is nothing but a sand. Okay, some of you might know that silicon, especially silicon material, is abundant in the nature. Okay, so all the sand, this is basically about silica. Okay, now if you look at in your daily life, okay, so this glass, okay, it comes under different form. Okay, one of the very common form is known as a quartz. Okay, quartz is also silica. Okay, then we have a fused silica. Okay, and then we may have seen soda lime glass or borosilicate glass. Okay, so they're all basically belong to the same category, silica, but they have a slightly some difference. Okay, so quartz is basically crystalline in nature, so it has a well defined crystalline structure. Okay, so we have a quartz here, and as you can see that all these arrangement of silicon as well as oxygen, they are arranged in a well defined manner. When we talk about fused silica, okay, it has a structure is amorphous in nature. Okay, so this we have a fused silica, but both quartz and fused silica are without any impurity. So you will not find any impurity. It will have only silicon and oxygen, right? So these quartz as well as fused silica, they are mainly applicable for those areas where we require a high temperature process. For example, most of the quartz tubes are used in a furnace where you have to subject temperature like 1000 degrees Celsius, 50 degrees Celsius, 2000 degrees Celsius onwards. Okay. Now, for most of the application in kitchen application, we are using soda lime glass, okay, or borosilicate glass. So they are basically amorphous in nature, but besides these silicon and oxygen, they will have some kind of a impurity. So for example, sodium hydroxide, we have a boron impurity, we have some calcium also, a lot of other things which are basically present here. So that is the main difference between these two materials. Okay. Now we know that the glass is an optically transparent material. Okay, this is one of the beautiful application. Okay, because of this particular property, glass is being used in display technology, right? Okay, it has a very good dimensional stability because it can, for example, survive with 1000 degrees Celsius without any kind of major problem. Okay, especially quartz and fused silica. It has a very good chemical resistance. So for example, if you look at glass, you probably have seen that these glass bottles are used to store acids like hydrochloric acid, sulfuric acid, and so on. Okay, we can also use, for example, this alkaline medium NaOH and KOH, okay, without any problem. Okay, so if you want to remove glass, the only acid which is basically used is hydrofluoric acid. Okay, so except hydrofluoric acid, glass has a very good chemical resistance with both acidic medium and alkaline medium. Okay, now applications, I will show you a couple of applications later, but display technology is becoming more and more popular. Okay, now people are talking about very big screens. Okay, so now we have 64 inches television, and for that we need a very flat thin piece of glass. Okay, so it is a very growing area, and I am going to mainly talk about this particular area here. Okay, now the challenges here, what are the challenges? Of course, we know that glass is brittle in nature. Okay, so it means that if you want to create any kind of a features, okay, it is more challenging compared to metals. Now you can always argue that you can use a diamond pen, or you can scribe it and then you can do that. Yes, of course, you can do some this kind of a simple structure. But if you want to create any kind of a complicated micro features whose dimensions are, for example, less than, let's say, 500 micrometer, okay, then it is more challenging task, because there is always a risk of breakage. Okay, so because of the brittle nature, okay, the glass micro machining is going to be a challenging task. Okay. Now, if you talk about MEMS, so my main research expertise lies in the MEMS field. So before joining IIT Bombay, I was working in an institute known as a VTT in Finland, where I was mainly a part of a MEMS team, which we used to develop MEMS sensors and wheel package. Okay, those who are not familiar with the MEMS sensors, okay, so you may have heard about something called accelerometer. Okay, now accelerometer, which is present in most of the modern cars, and this accelerometer is mainly used for airbag deployment. So wherever you have any kind of accidental chances, okay, you have an airbag which will basically open, and the device which is responsible for opening up this airbag is accelerometer. Okay, similarly, accelerometer, gyroscope, pressure sensors, they're all are available in our mobile phones. So when we are switching your mobile phone from horizontal mode to vertical mode, you may have noticed that the screen automatically tilts, right? It means that your smartphone knows that you are watching a screen in a horizontal mode or a vertical mode. Okay, so these are some of the devices which are basically comes under the category of a MEMS sensors. So pressure sensors, accelerometer, and third one is known as gyroscope. Okay, these are the three popular MEMS sensors which are finding a lot of applications in a daily life application. Okay, now these sensors, they basically works in a very low pressure environment. Okay, so what happens is that, okay, for example, here we have a symmetric picture here. Okay, so the device which is responsible, okay, here we have a MEMS device which is known as a MEMS accelerometer. Okay, and these moving structures, these devices which is indicated here, okay, so the entire MEMS device need to be packaged under a very low pressure environment. Okay, so for packaging application, people are using this kind of a glass wafer. Okay, so this structure here in blue color, it basically a glass wafer. Okay, what is the thickness of this thing? Okay, this thickness is roughly about 0.1 millimeter. Okay, this is thickness here. Okay, and what is the size, what is the diameter of this wafer? This is 200 millimeter. Okay, so now you can imagine that. Okay, so I am talking about a very thin wafer or substrate which is made out of a glass. The thickness is only 0.1 and diameter is 200 millimeter, sorry. Okay, and in this wafer there are thousands of such kind of a tiny through holes which are created in this thing. Okay, so this is one of the growing area where people are already working on, that how can we create micro holes, okay, on a large substrate, okay, using a low cost fabrication process. Okay, so this is one of the area. Other areas which are emerging is a microfluidics. Okay, so for example, for many of the biological application, okay, microfluidic application, Okay, so this is some of the devices which are being used. Okay, so currently people are using a polymer device like PDMS to create microfluidics. Okay, but if we can create the same kind of structure in glass, then it will have a lot of benefits. Okay, so people are thinking about, they're trying their best to create this kind of a structures on a glass substrates. Okay, so bio and microfluidics area is another application area where the tiny glass devices are needed. Okay, so let me show you on this thing. Okay, so I think some of you probably have seen. Okay, so this is a Samsung foldable phone. Okay, okay, now you can see that this particular screen here, okay, and this screen, okay, it is not a polymer screen. Okay, they are using a very thin, okay, sorry, this is ultra thin glass. Okay, so the glass is such a thin that you can easily bend it. Okay, so this particular product is already in the market now. Okay, and very soon this is some kind of application where companies like Samsung are working on that. Okay, so it's going to be kind of a transparent display. Okay, so right now this display is opaque, but very soon we will see a kind of a transparent display which will actually work in the same way where our normal phones are working on that. Okay, and again this is going to be a bit more futuristic device where people are talking about to create a mobile phone device, okay, which is bendable. Okay, so it no longer is kind of straight, you can bend it, okay, as you like. Okay, so very soon we will have more application where transparent display, okay, and flexible structure. Flexible structure means that depending upon what direction you can easily bend those things, and all these things are going to be made in a glass substrate. Okay, you have, most of you probably have already been familiar this Gorilla Glass. Okay, this is what you known as a scratch free glass. Okay, there's no scratch. Okay, no matter what you do, okay, it will not have any scratch. Okay, so companies like Corning, okay, the two famous companies, okay, which supply all these display to all the mobile phone company. One is known as a Corning Glass, second is known as Asahi Glass, which is from Japan. Okay, these are the two companies which supply the display, whether they are going to be used in mobile phone or tablets or in any other television display. Okay, so idea here is that right now in most application the glass is basically a flat. Okay, but if you want to create any, for example, you may have noticed that in our screen right now, if you go and buy in the market or as a mobile cover, you have this kind of a notch, right? So this notch is very simple example, but suppose you have to create a lot of this kind of a tiny holes, then which particular low cost process will be needed? That is going to be a different question. Okay, right. So this is the area where I was talking about earlier, microfluidics. Okay, we are in this last 2 years, because of the COVID situation, there has been a tremendous growth in this area. People are trying to fabricate or come out with something, a cheap lab on a chip application. Okay, so when we talk about lab on a chip, this is a very old term. Okay, so whether we can do all kind of a medical diagnosis on a small chip, which will give us a kind of a very fast results. Okay, so some of these structures, as you can see that from this image, people are already working on that. Okay, but mostly they are not utilizing glass, they are using a polymer known as a PDMS. Okay, because it is easy to create structure in a polymer compared to the glass thing. But idea here is that if we can create same kind of structure in a glass substrate, then it will offer you a much better results compared to the, okay, if you compare PDMS versus glass. Okay, as I have already mentioned to you, okay, that glass has a very good chemical resistance. Okay, but PDMS or any kind of polymer is not. Okay, so most of the polymers, they absorb moisture or humidity. Okay, and once they absorb kind of moisture, they will become basically swollen. Okay, same thing, you cannot use any kind of aggressive chemistry in case of PDMS. For example, let's say that for some application, if you want to provide any kind of acid, you cannot do that. But in glass, definitely you can do that. Okay, the optical transparency of PDMS is poorer compared to glass. So if you want to, for example, do any kind of in situ measurement, okay, then of course glass is going to give you a much better results. Okay, so because of all these reasons, glass is becoming very important, and I'm sure that within the coming few years it is going to be much more critical. Now when I talk about the traditional ways, okay, how we can create structures, how we can create this kind of vias, okay, or you can create this kind of a channels, okay, we have only limited choices. Okay, so for example, those who are from mechanical engineering field, manufacturing, you may have noticed or have gone through ultrasonic machining. Okay, we can use ultrasonic machining, we can use abrasive jet machining, okay, which can be used to create this kind of glass substrate. So idea here behind this particular technology is that you use abrasive particle, for example, like silicon carbide, okay, or for example, boron carbide, okay. All those harder abrasive particles, you can use it to create this kind of a structure, okay. But they have basically, the problem is that the aspect ratio is going to be very low. Now what is aspect ratio? So aspect ratio is defined as a term, as a ratio of the dimension, okay, in z dimension or depth wise dimension. Okay, so depth, and this is going to be xy dimension. So aspect ratio is basically a term which talk about the vertical dimension, okay, to the planar dimension. Okay, so if you look at the ultrasonic machining, abrasive machining, what is the problem is that they can only go for a up to aspect ratio of 1 or 2 or 3. Okay, but if you are to create a very fine through holes, then this kind of process cannot be used. Okay, again, if you want to create a very small dimensions, so for example, most of the abrasive which we utilize in mechanical engineering, they have a size which is more than 10 micrometer. Okay, right, so it means that if you use this kind of a 10 micrometer kind of particle, typically you will get about 100-200 micrometer holes. Okay, so if you want to go for a finer dimensions, then the choice you have is going to be laser ablation. Okay, so laser ablation is right now is the popular technique, okay, by which you can create these kind of structures in glass substrate. But the problem is that this is very expensive. Okay, so if you want to create through holes, okay, you have to go for a femtosecond laser. Okay, femtosecond means laser means that the laser pulse is going to be in order of 10 to the power minus 15 seconds. Okay, so you know that laser, depending upon the pulse duration, laser are also characterized by nanosecond laser, picosecond laser, and femtosecond laser. Okay, so this nanosecond laser, typically you can use it for roughening experiment, but if you want to create nice features, okay, you will have a problem. Okay, so these femtosecond laser, they are relatively very expensive. So just to give you an idea, a simple femtosecond laser ablation facility will easily cost you about 2 to 3 crore easily. Okay, and if we talk about within India, we do not have those many femtosecond laser facility. Okay, so not everybody can afford and can easily access the this kind of femtosecond laser facility. So idea, the question here is that, do we have any low cost, okay, any kind of a low cost alternative choice, okay, which can create structures in a glass based materials? And this is where this electrochemical discharge machining comes in picture. Okay, so before jumping in ECDM area, I just like to highlight one more time that what are the pro and cons. So these are the few facilities, the few techniques which is utilized in glass micromachining: abrasive machining, ultrasonic, laser, plasma etching, and ECDM. Okay, so they have some pro and cons, some positive points. So for example, if you look at abrasive machining, okay, if you want to create a large features, okay, then the process is definitely low cost, okay, and faster also. Okay, but it will not give you any kind of a very deep aspect ratio. Okay, nozzle clogging, those who are familiar, they know that this is a big problem. Okay, that in case of this abrasive machining, we are using this kind of a nozzle, right? So this, we have a nozzle inner wall, and these particles are coming from this. Okay, so ideally this opening size of this nozzle, okay, is relatively very small. So what happens that if you keep on using it, okay, these particle, they will basically block this nozzle, and you have to either replace it, okay, or you have to open it. Okay, so this is one of the problem. Same issues are also found in ultrasonic machining, okay, that it will have excessive tool wear. Okay, laser machining, as I mentioned, that it is a very popular technique, but the problem is that this is very expensive and not easily available here. Okay, so if you talk about industry, what industry is doing, they are working with both plasma etching and laser ablation process. Okay, so I'll come back to this point a little bit later, that what is the benefit of using ECDM, okay, for glass micromachining here. So let's talk about electrochemical discharge machining process. Okay, so first of all, this ECDM is a hybrid process. Okay, is a combination of ECM. Okay, so ECM stands for electrochemical machining, and EDM stands for electro discharge machining. Okay, so both electrochemical machining and EDM, they are basically well understood process within India. I think any bigger institute, they have either ECM or EDM. Okay, so both electrochemical machining and electro discharge machining, they are mainly used for electrically conductive material. Okay, so one of the fundamental condition is that the material, the workpiece which you want to machine, it should be electrically conductive, because workpiece act as one of the electrode. Okay, so this ECDM, as I said, that this is going to be a combination of ECM and EDM, and this ECDM is mainly used for non-conductive materials. Okay, because if the material is conductive, you can either use ECM or EDM. Okay, what kind of material we can do that? Glass, quartz, alumina, ceramic. Okay, all things we can do that. Okay, so this process is also known as a spark assisted chemical engraving. Okay, I will tell you what is the role of this chemical, which is very, very critical here. Okay, now what happens is that the process mechanism, okay, if you look at ECDM process, in the beginning it is basically about ECM. Okay, and let me just recall about the ECM process. Okay, so in electrochemical machining, what we have is this: we have the electrolysis process. Okay, so let me just tell you how does this electrochemical machining works. Okay, just for your information. So we have a cathode, we have anode. Okay, right, I'm talking about electrochemical machining. Okay, so suppose you want to remove a material. Okay, so that workpiece has to be connected to the anode. Okay, so what will happen here, we have some suitable electrolyte. Okay, and depending upon whatever material you are talking about, so let's say that this material here, it is going to be break into part, okay, some kind of ionic form. Okay, and this ionic form is going to react with whatever electrolyte you are going to have it. Okay, so for example, if we are using, let's say, iron here. Okay, for iron based material, we can use either sodium chloride or sodium nitrate. Okay, so either you will have a chloride or you will have a nitrate form. Okay, so this here, which is going to be form of Fp, okay, it is going to react with this and it will create like sludge. Okay, so this is the idea behind the ECM. Okay, so we are utilizing the principle of electrolysis. Okay, we are converting into the metal into metal ions and then we remove it. How about EDM? Let me just show you for those who are again. Okay, so let me just. Okay, so in case of EDM, okay, what we have here we are using electrolyte. Electrolyte means that this is going to be conductive medium. Okay, in EDM we are using dielectric, which is normally insulator, but if you apply enough electric field, then it is going to be broken here. Okay, so this is going to be negative. This is the workpiece. Again, this is going to be the workpiece, right? So idea here is that you have a dielectric. okay, and that dielectric, okay, will be broken down. So idea here is that every dielectric has some kind of a breakdown strength. So if you apply enough electric field, okay, this is very, very important. Normally people get confused, okay. So idea is that you need to apply enough electric field, not voltage, electric field, okay. So it is basically depend upon the applied voltage, depend upon what is the gap, okay. So either you can increase the voltage or reduce the gap, you will basically increase the electric field, right? So idea here is that if you apply enough electric field, then this dielectric will basically break it down, okay, and the electron will be discharged, and these electrons are going to hit the workpiece and remove the material by providing the localized melting and vaporization process. Okay, so these are the ECM and EDM principle. Now the question here is that how we can utilize in case of ECDM. Okay, so let me go to the next slide. Okay, right. So in case of ECDM, the workpiece is non-conductive. Okay, so workpiece is basically kept here, which is going to be non-conductive, right? Now we have a tool electrode. Okay, so suppose you want to create holes, so then tool electrode will be form of a needle. Okay, so whatever shape you want to replicate, okay, you have to first make the tool electrode according to that. Okay, now since the workpiece is non-conductive, so we have to utilize another counter electrode. Okay, so this is a counter electrode. Okay, so again, if you look at this thing, we have two electrodes, okay, which are connected with the power supply, and we are utilizing electrolyte. Okay, this is very important. Okay, so as I said in the beginning, the process is about ECM. Okay, and for ECM we need electrolyte. Okay, what kind of electrolyte? So typically we take alkaline medium. Okay, so alkaline medium means that we take DI water, and we need about 10 to 30% depending upon either NaOH or KOH. Right? So this is the electrolyte. Now what happens? So in the beginning, if you look at the process here, okay, when you connect to the power supply, what will happen? You are applying electric potential between this electrode and a counter electrode, right? So what will happen here? So since we are adding NaOH or KOH, it means that we are providing some ions here, right? Both NaOH and KOH are known as a strong alkaline medium. Okay, so what will happen here? Depending upon how much voltage you are applying, this water will go under electrolysis, right? So it will have H plus and it will have OH minus. Okay, now what we are interested in this H plus here. So if you look at the first step, we will have this kind of a process. So H plus, they will basically move towards this side, okay, towards the tool electrode. So whatever is the submerged area here, it will go to that side, right? So since this is a source of electron, okay, what will happen? These H plus, they will get electron from the tool electrode and they will make the hydrogen bubble. Okay, so this is what has been demonstrated in the first picture, that what will happen, okay, in the beginning of the process around the tool electrode, you will see that there are a lot of this kind of hydrogen bubbles which are basically accumulating near the tool electrode, right? Now if you increase the voltage, again what will happen? Okay, the process is going to be the same, but it will have the formation of H plus will be larger, H2 bubble will be larger, and slowly what will happen here is that these bubble size, they will basically grow in size. Okay, and after some point of a time, the bubble size will be such a large, then they will basically merge with each other. So it means that in the beginning we have these individual bubbles. After some point of time, these bubbles will basically grow up, and then what will happen is that we will have a continuous hydrogen gas film. Okay, so this is a hydrogen gas film which is shown in this picture here, correct? So now up to this part, ECM. Okay, now ECDM has done its role. ECM, electrochemical machining, has done its role. It has basically formed a thin gas film around the tool electrode. Okay, Now I want your attention on this picture again here. So now if you look at here, so we have a tool electrode, which is a negative. We have a hydrogen gas film, okay, which is work as a dielectric medium, and then we have an electrolyte, and electrolyte is conductive in nature, okay, and it is connected to the positive polarity. So it means that we will have this thing, okay, we have electrolyte. Now this situation is same as the idiom, okay. What is idiom? Two electrodes, and in between they have a thin dielectric, okay. So now the part of idiom will come in picture, okay, right? So you are applying the voltage. Let me just draw a picture of the applied voltage. So applied voltage is basically is okay like this, okay. So once you apply the voltage, depending upon applied voltage and this gas film thickness, okay, gas film thickness. So this is basically the applied electric field. Now, once this applied electric field, it is going to exceed with breakdown of hydrogen gas film. What will happen? The ionization process will start. So this breakdown, this gas film, it is going to be like broken down, and it will release the secondary electron. Okay. So as a result of this idiom, we will have the secondary electron. Okay. Now the electrons are going to move towards the positive side. Okay. Now, if you look at this picture carefully, we have kept this glass sample very, very close to the electrolyte, to the tool electrode. So what is going to happen is that this, okay, let me just draw a picture again just to demonstrate. Okay, so this is the tool electrode. We have kept the tool electrode very close. Typically, like the gap between this glass workpiece and tool electrode is either 0 micrometer, means the physical contact, or maximum 20 micrometer. Okay, so what is going to happen? This is the counter electrode. Okay, this is positive side, this is electron side. So electron is going to do, but since we have kept the workpiece very close to the tool electrode, these electrons are also going to hit the workpiece. Okay, so it means that electrons are also bombarding on the surface of the glass workpiece. Okay, I hope that this thing is clear. Let me find out a rough space so that I can draw one more picture just to demonstrate. Okay, so if you look at this picture here, ultimately what is happening is the following. Okay, that these electrons, okay, are hitting the workpiece. Okay, so slowly what will happen here, okay, that the temperature, okay, the temperature of the glass surface is going to go up. Okay, so from room temperature it will go up. Okay, and it can easily go, for example, up to 2000 degrees Celsius. Okay, and at this particular temperature, okay, some of the glass is going to be vaporized. Okay, some of the glass will going to melt. Okay, because glass melting point is roughly about 1700 degrees Celsius. Okay, and more importantly, glass will become softened. You know that glass has a glass transition temperature, right? So if you heat up the glass beyond 700 degrees Celsius, glass will become soft. Okay, so at that softened stage, the chemical rate, remember that we are using NaOH and KOH. Okay, so this chemical reactivity of alkaline medium with glass is very high when the glass will become soft, and then we will have the chemical etching. Okay, so let me just show you. Okay, so what I'm trying to indicate here, that the material removal is happening because of the localized melting. Okay, let me just draw a picture again. Okay, so if you look at, this is a glass. Okay, I'm drawing you 3 regions, 1, 2, and 3 regions. Okay, 1, 2, 3. So if the temperature of on the surface exceed with the vaporization temperature, so what is happening here in this zone, material is basically totally melted and vaporized. Okay, here in this zone the temperature is above the melting point, okay, but it is below the, yeah, okay. So it means that in this zone, the material is still in the molten stage, and this molten material will be removed by the electrolyte, flushing electrolyte, okay. And more importantly is this zone, the third zone, where the temperature is basically above the glass transition temperature, which is roughly about 700 degrees Celsius, okay. So here we have the chemical etching is involved, chemical etching, okay. So I hope that this thing is clear with everybody. Let me go back to the one of the slide which I think I have left over. Is this, okay? Right. So here is the some of the experimental images from my laboratory. Okay. So you can see that, for example, this is a tool electrode. This is its reflection. Okay. And if you can look at these numbers, okay, they are very fast. Okay. So we have the formation of the gas bubbles. Okay. Then gas film, and there is small discharge which is not probably visible, but it is normally happens near the tip. Okay. So because of this localized melting and evaporation process, okay, we have the effective material removal process. Okay. Now let me tell you that from our experimental data, we found that the role of the chemical etching is much more aggressive than the role of the electron bombardment. So mainly electron bombardment just raise the temperature of the surface, okay, and it is actual the chemical etching which basically is the main cause for the material removal. Okay, so what happens when the temperature is above 700 Celsius? That NaOH or KOH, it is going to basically meet with silicon oxide, and they are going to form sodium silicate or potassium silicate, which is basically nothing but a form of a sludge. Okay, so chemical etching. This is why if you look at all the literature, okay, the question here is that why we are using this alkaline medium? What if you use sulfuric acid or any kind of a salt solution? Okay, so ideally you can do little bit of machining using the acidic medium, but the rate will be very, very slow. Okay, so that's why most of the papers, especially in the glass medium and also in Elmuna, they are using this kind of a aggressive alkaline medium. Okay, so let me show you one video so that whatever I have taught you, it basically can explain. Okay, so this is a image from experimental setup. So what we are using here is not a single tip. Okay, so let me just show you first. So in our laboratory, we are mainly working for a array tool. Okay, so array tool means that we, in this example, this video, we have a 3x3 array, total 9 tips. Okay, so this is a tool electrode which is going to be connected to the negative terminal here. Okay, sorry, this is going to be positive terminal. Okay, here is the this one. Okay, sorry, I'm doing this little bit of mistake here. Yeah. Okay, this is negative terminal. Okay, this is a counter electrode which is going to be positive terminal. Okay, and workpiece is not visible here, but somewhat here we have the workpiece. Okay, which is nothing but a glass slide. Okay, and if I run the video, let me just show you. Please pay attention. Okay, so you can see that okay, as soon as you start the power supply, okay, we have a small tiny discharge which is taking place around this particular thing. Okay, and these tiny discharge are basically responsible for localized melting and evaporation process. Okay, so let me do one more time. Okay, so this is tool electrode. Okay, we have a counter electrode which we have kept in a form of a ring. People are also using a flat plate. Okay, we have some workpiece here, and electrolyte we are using is 10% KOH solution. Okay, one more time please. Okay, so depending upon what kind of shape you want to create, how many number of holes you want to create, okay, you can create a customized tool electrode and then you can use it for your machining applications. Okay, So this is a multiple through hole formation, and this is one of the, I would say, improvement we have done it compared to the work which has been done it before. So mostly people have only used a single tip electrode, and we have focused on the multiple formation of through holes. That has brought a bit more challenges. Okay. So now if I summarize it, ECM, EDM and ECDM, okay. So this is conductive medium, conductive workpiece, this is for non-conductive materials, okay. Material removal is totally dependent upon ionic dissolution, okay. Here we have a melting and vaporization process, but in ECDM, okay, the chemical etching, which is we call as a high temperature assisted chemical etching, that is the has predominant role, okay. Medium used here in case of electrolyte, here we have a dielectric medium, here we have a electrolyte again, okay. So this process is not about a discharge process, but here ECDM and EDM has some kind of a similarity, okay. So hydrogen gas, it is basically not desired, as you know that in case of electrochemical machining, okay, hydrogen gas is basically reduces the overall efficiency and causes problems, but in case of ECDM, that is the most important part, okay. So I hope that now you guys are clear about that, how this ECDM has some similarity and still some differences compared to ECM and EDM process. Okay. Uh, so we have also done some numerical modeling. Okay, so I'll just like to show you a little bit thing. Okay, so idea behind this thing is that suppose you like to know that what is going to be the roughly material removal rate, then idea is very simple. So you have a tool electrode, okay, and this tool electrode is basically a heat source, right? Because you are providing the applied voltage, as a result of that, okay, we have a plasma channel formation, and we have the electron basically which will come out, second electron, right? So this is a source of heat source, okay. So normally what people do that we take this Gaussian heat distribution, okay. Now what does it mean? So if you look at the tool tip, okay, for example, if this is the tool, okay, somewhat here, okay, we will have the peak density, right? So we have the peak intensity here, and as we go beyond the center line, we will see that the intensity of this overall heat intensity is going to be lower, okay. So this is a kind of normally people take this Gaussian heat distribution, okay, and this is the kind of a heat conduction equation. So this is going to be a transient heat conduction equation, so which is utilized to find out the temperature, okay. So the basic objective of ECDM process is to find out what kind of temperature is generated on the surface, okay. So if you look at this thing, okay, if you solve, we have a temperature here, x, y, and z are the dimensions. Alpha is going to be the thermal diffusivity, okay. So this is the same model which you can utilize is for drilling applications and also for the milling application, okay. So for example, we have mainly work to create through holes, but also on the channel formation, okay. So basic ideology here is that, okay, so this is the surface of the glass workpiece, okay. We need to find out what is the temperature distribution, okay. So for example, as I already mentioned to you that we are taking this Gaussian distribution, okay, something like that, okay. So typically we get three zones, which I think I have already explained in the beginning also, that 1 to 3. In zone number 1, the temperature is basically above the vaporization temperature of the glass, okay. In 2, we have above melting point but below vaporization temperature, and this 3, which is very very important one, where the temperature exceeds the glass transition temperature here. Right. So now, if you look at simulation, it's basically up to you, right? So how do you define which particular model you pick up and what are the conditions? So if so, by knowing this kind of a temperature distribution, you can find out, okay, that what is going to be the material removal rate, okay. Now let me just tell you that typically these experimental results, okay, which you are obtaining by performing experiments, they typically do not match with what has been reported by the simulation thing. So if you look at simulation will give you some kind of temperature distribution, okay, but mostly it is not going to be matching with experimental data. So here are the two very important points, and this is also the main bottlenecks in this particular field. Okay, so now if you look at this side here, I have drawn you the voltage versus time graph here. So in ECDM case, mainly we use a pulse power supply. We do not use DC continuous power supply. We use pulse. So pulse info means that this voltage will be on for a certain period of time and off for a some time. So during the off period, what happens is that, let me just draw another picture. So this is the workpiece. I'm drawing a plasma channel, something like this, right? So during the on period, we have the plasma channel. Plasma channel means that we have a discharge process, right? Now, during when the there's an off period, there's no plasma channel, and whatever is the electrolyte which is waiting outside. Okay, so this is the electrolyte here, electrolyte. Okay, so during the off period, the electrolyte basically goes inside the gap and remove all the material. Remove material is that the region where you have the melting or molten pool. So that molten pool material is typically removed here. Okay, and during this particular period, we also have some chemical etching. Okay, so during the off period, both the molten material is removed and also the chemical reactant is also removed. Okay, now what happened is that during the simulation work, people assume that whatever is material whose temperature exceed the melting point. I'm talking about zone number 2. Okay, so whatever region where the temperature exceed the melting point, that the entire part is removed during the off period. Okay, this is one of the basic assumption. Most of the researchers take that. Okay, so it is assumed that whatever, so this entire portion, okay, which I am drawing here, is removed during the off period. Okay, but this is never true. Okay, so this part, this parameter is known as a flushing efficiency. It means that during the off period, people assume that 100% material removal is taking place, okay, from those regions where the temperature is above melting point. Okay, but in practical concentration, this is very small. Okay, let me just tell you idea. So for example, in our laboratory work, we are using from 1 to 10 kilohertz frequency. Okay, 10 kilohertz means that 10 to the power 4. It means that within a 1 second, we have 10,000 cycles. Okay, so we have 10,000 cycles. It means that one cycle is going to be 0.1 millisecond. Now you can imagine that. Okay, if you take a 50% duty ratio, okay, the pulse off period is 0.05 millisecond, which is very small. Okay, so it means that during the practical application, the electrolyte does not get enough time to remove the entire portion of there. Okay, so flushing efficiency is never 100%. Okay, but it is extremely difficult to find out in simulation that what is going to be the flushing efficiency. Okay, so because of this particular parameter, the simulation results never match with experimental data. What people do, okay, so they get some parameter and then they do experiments, and after that they try to match the experimental data with simulation data, okay, by taking the different values of. So in literature, people have reported from 5%, okay, to 25%. These are different values of the flushing efficiency. People have basically chosen it. Similarly, if you look at the another parameter is the partition energy. Okay, it is in simulation you are assuming that all the energy which is coming from the heat source is actually utilized in heating up the substrate. Okay, again this particular thing is not true, because this will depend upon a lot of like convection heat transfer, okay, which is again a difficult parameter to find out. Okay, And this is also where people have taken the different values of the. So because of the two parameter, partition energy and flushing efficiency, there is some kind of scope for a research. If somebody can really come out and tell that what is going to be the average amount of partition energy and flushing efficiency, then this is going to be a very, very good study. Okay. So again, so for example, if you look at this case, so okay, so this particular numerical model basically shows about a microchannel formation where we have considered the moving heat source. And in this picture, if you look at this half sphere profile, okay, this profile basically tells the numerical profile, and this data here, okay, it tells you the experimental data. Okay, and you can see that the profile which is predicted by the numerical simulation is an ideal profile, and it really does not match with the experimental results here. Okay, so this is one of the area where a lot of people are working on to solve this problem, and this is one of the big research gap in the field of ECDM area. Okay, now having said this about the basic fundamental, let me just go through about the application side. Okay, so as I said that I am mainly working in the field of MEMS area. Okay, and this is one of the microstructure device. This is a 3D inductor. Okay, as you know that inductors are basically used to store the energy in magnetic field. Okay, they are also utilized in our tube lights and so on. So we wanted to fabricate a very small 3D inductor on a wafer scale. Okay, so dimensions of this inductor is within 500 micrometers. So they are very large. Okay, but we wanted to fabricate using the ECDM process. Okay, so why we are calling as a three-dimensional 3D? Because we are utilizing the both surfaces of the substrate. So this is front side as well as the back side. Okay, so this is why we are calling as a 3D inductor. And in order to create 3D inductor, one of the most challenging tasks was to create this kind of a through holes. Okay, this kind of a through holes in a glass substrate, and this is where we have utilized ECDM process. Okay, so what? Okay, so let me just talk about a little bit of the setup. Okay, so since the ECDM area is still in the research field, we do not have any commercial setup available in the entire world except one country, one company in Switzerland. Okay, so that is a startup company, and they are trying to sell some of the ECDM setup. Okay, but those are very, very costly. So what we have done is that we have developed our own setup here in IIT Bombay. So we have a 3D basic moving setup. So this is coming from Hallmark. Okay. Then along with that, they have also given us this kind of a controller. And this is a pulse power supply, which is the expensive part. Okay. So this pulse power supply can go up to 100 kilohertz. Okay. And it can also provide you a large amount of a current. Okay, so this is basically about a 200 volt to 20 ampere pulse power supply. Okay, that is the two important parts. So if we have a 3D motion controller, okay, XYZ table, and this XYZ, it has a resolution of 1 micrometer. So it means that precisely you can move in all three directions. Okay, then we have a simple electrolyte circulation pump. Okay, and other things as well. Okay. So now, as I said that we started with mainly we are working on this multi-array tool, but we have also started with a single tip electrode, okay, made by electrochemical machining. And if you look at the size here, it's a 70 micrometer. Okay, so this is where the idea about ECM and its importance will come in picture. So mainly we are working with this kind of array tool. Okay, so 3x3, 6x6, 5x5. Okay, we can create all kind of a customized tool electrode using a wire EDM. So wire EDM is one of our main challenges or main equipment which we are using it. Okay, so idea behind is that it is very simple. So using the wire EDM process, okay, you can create this kind of a array tool. Okay, so first you have a wire. Okay, we are using this molybdenum wire machine here. So you can create this kind of a tool electrode. Okay, the important point here is that why we are using wire iridium. Okay, the dimensions are very large. Okay, so for example, here we have a 15 millimeter. The height of these two electrodes is 15 millimeter. Okay, and at the tip size, this one is a 0.15. Okay, 15 millimeter. So you can think about it. This is we are talking about. Yeah, so the aspect ratio of these tools, okay, is roughly closer to 100. Okay, so such kind of a high aspect ratio tool electrode cannot be created by any other technology. Okay, so that's why we are using this kind of a wire tool. Okay, so other thing is that these tips, they are tapered in nature. Okay, so here the dimension is 150 50 micrometer. At the base, it's about 700 to 900 micrometer. Okay, right. So let me just show you some more pictures. This is the actual pictures of the tool electrode. Okay, so as I said, 15 millimeter here, 3 by 3 tool electrode. We can create. Okay, so these are some of the images of the tool electrode which we have made it. Now, depending upon what kind of a device you want to create. So, for example, this 2 by 5 array device, this is mainly used for inductor application. Okay, inductor application mainly, and this is mainly for process development. Okay, so mainly we are using stainless steel as a tool electrode material. From our basic experiments, we have found that SS is very good material. In fact, it is better material than like molybdenum and tungsten. Okay, from our basic fundamental study, we found that tool wear of SS is much lower compared to tungsten. Okay, which tungsten has a higher melting point, but still it has basically a lower tool wear. Okay, that is very good result from our side. After that, once you create this kind of a tool electrode, we have seen that the surface roughness, okay, the surface roughness of this tool electrode is also a very important parameter. Okay, so if you compare with ECM and EDM machine, okay, typically the tool roughness does not come in picture. Okay, but in case of ECDM, this is one of the main point here. Okay, so if you look at the surface roughness, okay, it is one of the deciding factor in case of ECDM. Okay, so what we have done, we have created different tools having varying surface roughness. So we have changed the wire EDM parameters. So by changing the wire EDM parameters, you can create different roughnesses. Okay, and we have shown that later that the surface which will have a high surface roughness, okay, it will create holes having a larger overcut. Okay, so idea here is that if you look at these two pictures, okay, high surface roughness and low surface roughness. Okay, so your low surface roughness. So for example, 10 micrometer here, this is roughly about 1 micrometer. Okay, so what will happen here? So remember that in case of ECDM, the entire process is depending upon the hydrogen gas film. Okay, because the gas film is going to be broken down during the process. Okay, so if you have a high surface roughness, okay, the film thickness of or average film thickness of hydrogen gas film is also thicker, right? So this thickness is also going to be more than this case. So it means that if you are going to apply any kind of a fixed voltage, okay, the process may not be that enough. So what we have seen here in that in case of high surface roughness, the spark are very violent in nature. The discharge which is taking place, okay, they are more aggressive compared to a thinner case here. And those aggressive discharge are basically causing a larger overcut, which I am going to show you in the next stage. Okay. So what, as I said, that by changing this kind of parameters in case of wire EDM, okay, so machining current and pulse on duration, these are the two important parameters in wire EDM, and if you can change that, you can create different kind of roughnesses, and those roughnesses you can basically utilize it. Okay, so what we have done it, we have first created this kind of a tool, and after that we have used electrochemical machining or electrochemical finishing process, okay, to create this kind of a nice tool. Okay, so by controlling the roughness, we were able to study what are the fundamental aspect on the whole quality. Okay, so for example, look at this thing. So this is the picture after viridium. Viridium means that after fresh wire is formed, and this picture is after the electrochemical finishing. Okay, and you can see that, okay, that roughness has drastically reduced, and using this kind of a tool, okay, we are able to get a very good quality of the through holes. So let me directly jump here. Okay, so these are the holes number 1, 2, 3, 4. If I go back, okay, this is the tool number. Okay, this is the surface roughness. Okay, after fresh viridium process or fresh tool, after doing the first ECDM, okay, after using electrochemical finishing process, and so on. Okay, so the basic ideology here is that we wanted to investigate that what is going to be the effect of the surface roughness on the whole quality. Okay, and compared to, if you look at this thing, we have got the best result for that particular tool, which has considerably lower amount of a roughness value here. Okay, so this is one of our conclusion. Okay, again, I think this picture I have already indicated here. So we have done a lot of experiments, so I'm not going to talk about the process parameter effect, but yes, if you have any questions, you can always refer to these journal papers, okay, or you can always contact me. Okay, so using this kind of a 3x3 tool array and then 5x5 array, okay, so my students, they were able to optimize the process, and the typical dimensions or the minimum dimension which we were able to get it is roughly about 250 micrometer. Okay, it is not possible to get dimensions which are lower than that because of a tool conditions or tool restrictions here. Okay, so we were able to create this kind of a through holes. Okay, and after that we try to create this kind of a through glass via. Okay, through glass via, or this is also indicated as a interconnections. Okay, so this is a 3D interconnects. Interconnection means that it is basically a some kind of wire through which electrical signal can be passed. Okay, so the fabrication process is shown here. So idea here is that first you create this kind of a through holes in a glass. This is a glass substrate. You create through hole by ECDM process. Okay, and after that, using copper electroplating, okay, you can fill copper here in these through holes. So this is a copper electroplating. Okay, okay, so if you look at this kind of thing here, if you pass electric current, because copper is a conductive in nature, electric current will pass through. Okay, so this is why this is known as a 3D or three-dimensional interconnections. Okay, so once we have created this thing, then we have formed this kind of a copper RDL. Okay, so if you look at this structure here, if I provide, let's say, a potential here, the current will pass through with medium, will go up, pass through. Okay, something like that. Okay, so this is what it structure basically looks like here. Okay, so we mainly work in this area. Let me just show you some of the results. Okay, so this is through holes. Okay, this is the cross section picture here of the wafer. Okay, so we were able to make on the entire substrate. Let me just show you. I think it will be a picture. Yeah, I think this picture is probably better. Okay, so we started with a fresh wafer. Okay, so this is a 2-inch glass wafer, fused silica substrate. Okay, and using this 3x3 array, we have first created this 1, 2, 3, 4, 5, 6, 7, 8, 9. We have created total 9 tools. Okay, so through a formation, then we have bonded with a copper tape. Okay, and if you look at this side, it will look like this. Okay, so you have copper tape, we have this glass wafer, okay, and if you connect in copper electroplating, copper will basically form like that, okay. So this picture here indicate that copper is completely filled with through holes. After that, we have basically polished it, okay, and it looks like something like this, okay. So this wafer is a copper filled PGV, okay. And let me show you some more pictures, okay. So now here we have only like demonstrated the process that copper is working fine. We have done some material characterization, electrical characterization, okay. But after that we wanted to make a device, okay, inductor device, and for that we have used a different tools, okay. So tool is this one, which is going to be a 2x5 tool, okay. So again, same with the Viridium process. Using that, we are able to create like 1, 2, 3, 4, 5, 5 tool. They look like this. Okay. If you look at the zoomed view, okay, because of the tapered tip, okay, the opening size is also tapered in nature. Okay. Okay. Now, after that, using the same process, we have deposited copper inside the through holes. Okay, so all these through holes were completely filled with copper. Now, very important thing here, those who are from electrical engineering, okay, you know that glass is a non-conductive in nature, right? And copper is going to be a conductive medium. So it means that from here to here, we will not have any kind of a electrical signal. Okay, there's no electrical signal will flow. Electrical signal will only flow from bottom to top. Okay, and it is how basically looks like. Now the profile is looking something like this because not because of the process, but because of the polishing. Okay, you know that glass is again hard material, so it is very difficult to make the cross section like that. Okay, because this is all done by manual process. That's why the profile looks like this. But in generally the profile is going to be this kind of tapered in nature. Okay. So after that, what we have done, okay, that we have created this kind of a spiral structure. Okay, so this is a spiral. Okay, this is what is known as a toroidal inductor, and these are same 1, 2, 3, 4, 5, 6, 7, 8. These are same holes on which we had formed. Okay, so idea here is again very simple. Once you have created this kind of a copper deposition, after that you have to simply make this kind of a copper RDL by using the standard lithography approach, okay, which we have done here in case of CN IIT Bombay. Okay, so here we have total 10 through holes. In this case, we have only 2, 1 and 2 holes. Okay, so this is showing you the front side of image. This is showing you the back side image. Because glass is transparent in nature, you can see both front and back side. Okay, then we have done some electrical characterization to find out what is the resistance, okay, how the resistance is varying with number of loops, and this is the result. So we have got a very good electrical characteristics. It means that all these through holes, okay, which is filled by copper, is showing kind of a ohmic interconnections behavior. Okay, some more images from the same wafer. Okay, right. So as you can see that this design is different. Okay, this is same as the like which I have indicated in earlier slides. Okay, so we have done a lot of experiments by changing the shape of the inductor. Okay, and so all these different sorry devices have been fabricated by using the same low cost method. Now idea here is that via formation is low cost ECDM approach. Electroplating is also inbuilt. Okay, we have not really used any kind of expensive process, but to create this kind of a simple devices by using this method. Okay, now let me just show you. Okay, so now if you look at this work, okay, so far we have only shown you the application of drilling application. Okay, now let me tell you something also about a milling application, okay, or formation of the planar structure. Okay, So suppose for some application you want to create some kind of micro channels, okay, for let's say microfluidic application or biological application. So idea here is that, okay, using the same process, okay, you can create different kind of a channel. For example, so the tool is here, okay, you can create, if you move the tool electrode here, okay, you will get this kind of a depth, okay. And if you want to go for a deeper things, what you do, you have to use a multi-pass approach. Multi-pass approach means that you first go this side, then you bring down the tool downwards, okay, then come back again, okay, and you will have the formation of this. So using this kind of a multi-pass approach, okay, it is possible to create microchannels having the different depths, okay. So here, for example, if you look at the picture here, okay, the sample here is 1.1 millimeter thick. This is the standard glass slide which people are using in biological application, okay. So by using this kind of approach, it is possible to create any kind of a microchannel depth, okay, straightforward. Of course, I have not indicated in detail, okay, but as I mentioned that chemical etching, main process or main mechanism here is chemical etching. If you increase the concentration, okay, of course, chemical etching rate will be go up, okay. So if you want to, let's say deeper through holes, what you have to do, you have to use a concentrated KOH, for example, 30%, okay. Right? If you want to go for a shallow one, you can either use a like low concentration electrolyte, okay, or you can use high concentration with lower number of passes, okay. One more thing, okay. So again, in the beginning, if you can see this picture, okay, we have only created a single channel, okay, by using the normal needle, okay. So the normal needles which is we use in cloth stitching application. So we have utilized this kind of a tool electrode which is very low cost. But if you want to create multiple channels, okay, then again this is a line array tool. So earlier I had indicated about a area array tool, okay. But if you want to create a large number of through hole or channels, then you can create this kind of a line array tool electrode, okay. Again, some of the process capability, not only because the setup having a 3D XYZ system, okay, you can just program CNC programming, and you can create not only straight channel but spiral channels. You can create zigzag channels or any kind of a shape. It is possible to be created by using this kind of a process here, okay. So the process is very flexible in nature, okay. And whatever shape you have, whatever design you have, okay, how many number of channels you want to create, the only thing you have to do is that depending upon your requirement, okay, depending upon your requirement, you have to first create the tool electrode, okay. So for example, in this thing 1 2 3 4 5, okay, I wanted to create 5 channels, okay. So one approach is that you do one electrode, do it 5 times. But what we have done, we have created this kind of a 1/5 electrode, okay. For example, here you have a 10, here you have 5. If you want different widths, okay, the only thing which you have to do is just change the tool dimension, okay, and you will have your things, okay. Let me just show you, okay, couple of more examples, okay. We have also created this kind of inductor. We are also currently working on a fuel cell application, okay, which will have this kind of a double-sided channels here, okay. So all these things are currently ongoing work. Let me tell you just thing. So we just wanted to demonstrate a device for microfluidic application or biological application, okay. So this entire device is fabricated by using the ECDM process. So what we have done, we have taken the standard this wafer 1.1 millimeter thick, okay. We have first created this kind of a large through holes, okay. So typically people mainly focus on the micro holes, but if you want to create both micro features as well as the macro features, then how will you do that, okay. So we have created this kind of a through holes. The dimension is roughly about 5 millimeter, if I remember correctly. Then we have connected these things with the channel, okay. So this is, we have a channel, okay. So total is 1, 2, 3, 4. This is about 10. So we have used 1 by 10 tool to create this kind of a thing. And after that, we have made it device. Now we wanted to see whether this kind of device will work or not. Okay, so what we have done, we have temporarily bonded this chip to another flat piece. Okay, so bonding was not perfect, but let me just show you some of the initial results. Okay, so we have dropped one thing. You can see that how quickly this colored water is traveling. Of course, the bonding was not perfect. That's why there's some interface, there's a small leakage. But more importantly here is going to be, so in the beginning of the process, you can see that the fluid was moving very fast, but as we are not utilizing any kind of a pressurized flow, okay? In real application, in real biological application, fluidic application, you have some kind of pressurized pump, okay, which is responsible for moving the thing. But here, the entire fluid is moving because of the self-gravity, okay? You see that now it's basically reaching towards the end, okay? So we are very, very confident that this kind of a device will work, okay? And we are mainly working on this side. So let me just run you one more time so that those who have not paid attention, they can also look at here, okay? So we are just simply dropping it, okay? Within 30 seconds, okay, the fluid is basically moving from this to top end, okay? The total distance it has traveled is more than 100 millimeter, okay? So this was roughly about 5 millimeter, one channel length is roughly about 10 millimeter, there are total 10, yeah, more than 100 millimeter it has traveled within 30 seconds, okay, without using any kind of a pressurized flow, okay? So this is one of the area where we are very much excited right now, okay? And we are trying to find out new application using this kind of a simple low cost methodology process, okay? Let me just see. Okay, fine. So far I have indicated only about the glass. So this is one of the just slide just to indicate that using this kind of ECDM technology, okay, not only glass, but also we can machine alumina. So normally this alumina machining is also not easy. Okay, again same thing. Alumina is more having a higher melting point, even hardness is more than glass material, okay, and chemical etching, okay, of alumina is more difficult, okay, alumina is much more challenging, okay. So using the process, okay, we were also able to create this kind of a thing, but of course this is much more challenging and we are currently on working on that. Now let me just inform you, now alumina, okay, and glass, they are similar in nature, okay, but alumina has a one very important characteristics, okay. So glass is a thermally insulator material, but but alumina is not, okay. So it can be used for those applications where we want to take away heat from some of the localized spots, okay. So where we require high temperature stability, okay, electrically insulative nature, but thermally conductive thing. Then for those applications, alumina is being utilized here, okay. So this is one of the area where we are currently working on that, and those who are interested, okay, they can also look forward for micro machining of alumina as one of their potential topics here. Okay. So with this, I think my 1 hour 30 minutes is about to be over. Okay. So I just like to summarize here that ECDM is a low cost alternative. Okay, is a low cost alternative to a laser ablation process. Okay, but of course I cannot say that this is superior because it has a challenges. Okay, the feature size, okay, has to be more than 250 micrometer. Laser you can go for, I think, up to 50 micrometer people have demonstrated easily, not a problem. Okay, but the point here is that especially within Indian academic context where researchers do not have a direct access to laser facility or femtosecond laser facility, okay, this ECDM can be easily a low cost setup. Okay, the setup cost is not very expensive. Okay, so for example, the setup which I had shown you here, it is causing me something about 7 to 8 lakhs rupees. Why? primarily because of the power supply. Okay, power supply was the most expensive, almost 4 lakh was power supply. But if you do not want to go for a area array tool, if you want to stick to a single tip, then you can use a normal, I think 5 ampere 60-volt power supply is going to be more than sufficient for you. Okay. So ECDM has a certainly advantage in that way that you can easily low cost, low maintenance thing. Okay, the electrolyte which is required is also quite easily accessible. Okay, sodium hydroxide or potassium hydroxide. Okay, features people can figure it out. And right now our limitation is roughly about 250 micrometer. We have some idea how to reduce the size further, but we are still working on that. Okay, so both through holes, single holes, array holes, planar structures, okay, channels of varying depth, you can create it easily. Okay, and now in principle, it has a lot of applications, especially for fuel cell application, where right now people are using these metallic channels, okay, but it's very difficult to find out what is happening inside it. So if you can use the same process for microfluidics or fuel cell application, because of optical transparency, it is going to be very easy to observe that what is happening, what kind of calculation is happening here. Okay, so it is going to be very, very easy from that point of view. Okay, now I have not indicated here about the direct formation of 3D MEMS devices, but yes, in principle, you can also utilize that. Okay. Right. Okay. So at finally, whatever work which I have shown you here, okay, it is funded by this Ministry of MHRD, okay, under this imprint project. Okay. So imprint project is basically funded by these two institutions, and most of the research work which I have indicated here, it has been carried out by my students. So I really like to acknowledge them in that way. Okay, so with that, I am finishing my presentation. If you have any questions, okay, you can basically contact me here. This is my direct mobile number. Okay, you can contact me. Okay, now I think the floor is open for questions. Let me see.
Okay, sir. Thank you so much. So I would like to ask the participant, is there any question you want to ask?
I'm not sure whether the guys have understood.
Hi, sir. Sir, am I audible? Yeah.
Yes,
Sir,
yes,
myself
yes.
Vishnu. So I'm actually from Kerala. So
Okay.
I have a small doubt, sir. Is there any dedicated studies to analyze the nature of toolware? Because like in array tools, it is going to be different, right, sir?
Yes, yes. So, may I first request those who have opened their mic, can you please mute yourself? Because it is good, not noisy. Okay. So, yes, so the toolware is going to be very, very critical point here. And in a single tip electrode, it does not matter, right? But when we're talking about this area array tool electrode, the toolware is extremely important. So what we have observed here is that those tip electrode which is on the periphery, it has a slightly higher tool wear. Okay, and the ones which are in the center, it has a relatively less thing, because in ECDM process, okay, the current density is going to be more localized on the periphery point. Okay, so from that point of view, it is going to be there. Another thing is that, which I have not indicated in this presentation, okay, that the gap between the workpiece and the tool electrode is extremely important. Okay, and if the workpiece tool gap goes beyond 20 micrometer, then the machining will stop. Machining will not take place. Okay, it automatically means that whatever is the tool wear, it has to be within that particular 20 micrometer range. Okay. So how we are doing it? That after doing 3 or 4 rounds, okay, we are doing polishing. Okay, we are basically using a tool electrode and we are polishing it so that all the tips can be brought to the same level. And after that, we are performing electrochemical machining to reduce the size of those. Did I answer your question?
Yes, sir. Yes, sir. I got it. Thanks. Thanks.
Another thing which I have indicated only for like briefly is that we have taken 3 or 4 different materials, right? We have taken stainless steel, molybdenum, and tungsten, and up to our surprise, we found that SS is doing much better than tungsten, although tungsten has a higher melting point. Okay, so the reason is that we have seen that during the ECDM process, okay, that around the SS electrode, we have some kind of a coating which is formed as a result of the reaction product, and this coating is kind of preventing this tool wear. Okay, but in case of molybdenum and in case of tungsten, okay, we have not seen this kind of coating. So we have just published this work on the tool wear in Journal of Manufacturing Process, and I will be happy to share that detail about that process with you. So you can contact me. I will share you that paper.
Definitely, sir. Definitely. Thanks.
Is there any question from the participant? Okay, sir. Thank you so much. Thank you so much for accepting our request and presenting and explaining about this ECDM processes and giving so much information regarding this process, which is an
Certainly.
which is a hybrid process. And sir, you have explained this micro machining of mainly brittle materials like glasses. Most of the experiment you have done on the glasses, and also you have explained the application of glass in microfluidic. Then the benefit of ECDM over ECM, over AJM, abrasive jet machining, and ultrasonic machining, laser beam machining, and also you have gives details on the ECDM process, multi-hole formation, multi-tip array, tool fabrication also you have told, and numerical simulation of this ECDM process you have also told. And also you have explained details about the fluxing efficiency and this partition energy, which play an important role for the ECDM processes. And sir, the formation of through hole glass and sir, through glass wires using MEMS, and sir, also 3D inductor formation in fused silica also you have explained, and also you have told the application of this in bio or microfluidic application you have also explained. Thank you so much for thank you so much, sir.
Certainly, Lalit. So just one request that if anybody is interested in knowing more details
Yes,
about
sir.
glass micromachining process or micromachining of ceramic material, please
Okay,
do
sir.
not hesitate in contacting me.
Okay, sir.
Normally,
Definitely.
whatever I have seen that people just attend this FDP program,
Sir.
but I do not know. For example, one participant is asking question on rotary friction welding.
Yes, sir.
I do
Yes,
not
sir.
I do not know how this rotary friction welding is related to my presentation.
Okay, sir.
I'm not sure. Yeah. Okay. So if there are any other question, you can always contact me. Okay.
Sir, sir, definitely, sir. Definitely,
Sure.
sir. Thank you so much, sir.
Sure.
Yes,
Thank
sir.
you very
Have
much.
a nice day, sir.
Yep. Thank you.
Bola, sir.
participant already we have.
Hello everybody. Good afternoon to one and all. And Prashant Sahu sir is now online and he's ready to give the talk. So we'll start our day 2 session 2 of this faculty development program. Namaste sir. Good afternoon sir. Okay sir, thank you so much for sir coming. And so sir, Professor Prashant Sahu, Jadavpur University, will give a talk on tribology of metal matrix composite. And this is the brief introduction to Professor Sahu. Professor Sahu holds a PhD degree and an MTech degree from Indian Institute of Technology, Kharagpur, and bachelor degree from Jadavpur University, Kolkata. Currently, he is professor at Department of Mechanical Engineering at Jadavpur University, Kolkata. He has more than 25 years of teaching and research experience in the field of manufacturing, materials, and mechanical engineering, with special emphasis in tribology of materials. He has guided large number of PhD and master's students as well as coordinated and participated in several financed research projects. He has worked as evaluator of projects for international research agency as well as examiner of PhD thesis for many university and institutions. He is on the editor board of several international journals and conferences. In addition, he has also authored 2 books, edited 3 volumes, written over 30 book chapters, and more than 500 articles in peer-reviewed journals and conference proceedings. And adding to his achievement, he has H-index 30 plus and citation more than 5,000. Professor Sahu has been ranked among top 2% global scientist list prepared by Stanford University. In recognition of his teaching excellence, Professor Sahu has been awarded INSA Teacher Award in 2021. Thank you so much, sir, for coming to this FDP Faculty Development Program. And sir will give talk on tribology of metal matrix composites. Okay, sir, it is over to you, sir. You can start now.
Thank you, Dr. Deo. I think I am audible, no?
Yes, sir, you are audible, sir.
Okay. Thank you for your kind introduction, and it is always a pleasure to reach over to the faculties and my colleagues.
Yes, sir, thank you, sir.
Unfortunately, in this in this platform, it would have been really good if we could have met in person, and I hope we will be able to do that in near future. Regarding my presentation, let me share my screen. I hope it is visible to all of you, okay?
Yes, sir. Yes, sir, it is visible, sir.
So I will be talking on tribology of metal matrix composites. Since I am a man from the area of tribology, so I cannot just avoid tribology in any of my lectures. Okay. So here I will be talking about a little bit of introduction to your composites, then metal matrix composites, and then their fabrication procedures, and finally I will move to some of the avenues regarding the tribological characteristics that we have done here at Jadavpur University. I will try to restrict my lecture maybe in 1 hour to 15 minutes time, and then we will have some 10-15 minutes of discussion. Now, why tribology? I always show this introductory slide in all my lectures just to introduce to the audience that why this tribology is so important. We all, I assume, either from a mechanical background or from manufacturing background, even if in any other engineering field as well, what we are dealing with, we are dealing with basically machine components. And the machine component, the machine is a utility through which actually we transfer some form of input to some other form of output variable. That input may be in the form of different type of motion. It may be some kind of sequence of motion, then different loads, velocity, temperature, loading time, etc. And then as output, the our desirable output, it may be in the form of some amount of force, some definite kind of motion, or the combined force and motion combined, that is the energy. So basically through these machine components, what we are doing, we are transferring some form of motion or energy or load to some desired form which I need for my particular purpose. In doing so, in between, what we use is the machine component. And in that machine component, we will always have the bodies in relative motion. The two bodies, if they are not in motion, it becomes a structure or foundation. Here, what we are dealing with is the bodies in relative motion. And when the bodies are in relative motion and it is performing the job, that means it is converting the input variable to some form of output variable, that becomes a tribotechnical system. Tribo is basically the contacting surfaces. So tribology is the science of contacting surfaces. Now, when we are doing this conversion, always the efficiency will be less than 100%. Output will be much lower compared to our input. And that is typically because of the losses from the system. And those loss variables, they appear either in the form of friction or wear or both. Friction, it is the resistance to motion, which gets dissipated in the form of heat or vibration or acoustic emission. And wear, it is the loss of material from the surface, and or there will be some degradation to the surface as well. So these are the two loss variables, and they will always be there in the system. And as a result of that, what happens, whatever input we are providing to the tribotechnical system, the output will be lower than that. Now, if I want to increase the efficiency of the system, then I need to minimize or I need to control these losses, friction and wear. And herein lies the need for the study of tribology or knowing the tribological processes. Obviously, if we look at the machining processes, they actually comes under the purview of these loss variables, but in that case it is not loss, it is the desired output, because they are the wearing out of the material from the surface. By doing that, that is the beneficial aspect of this wear. So I will not be talking in that domain, that how this wear can be used for your beneficial approach towards tribotechnical systems. What I will be dealing with is the minimization of this friction and wear, or the tribological aspects. Now, regarding this tribology of metal matrix composites, to just start with a brief introduction to the composites, we all know the composite is made up of at least two materials. They must be distinguishable at least at the macroscopic level, and the desire is to have superior properties, which is the combination of the properties of those constituent materials. And then the composite will have at least distinct phases. It can have continuous phase like matrix, and then there must be some dispersed phase that is in the form of reinforcement. Obviously, the matrix that acts as a binder or as a support. And on the other hand, these reinforcements are chosen in such a way that I want to get improved mechanical properties. Obviously, these composites are abundant in nature as well, and everywhere in bone structure, wood structure, everywhere we will have this combination naturally. And when we talk about the material synthesis, obviously depending on the properties we look at, we can choose these reinforcements and matrix, and accordingly we can design the composite material. So these when we talk about the reinforcements, the nature of reinforcement, based on that, it may be particulate, it may be discontinuous fiber, it may be continuous fiber. Obviously, with the change in the geometry of the reinforcements, obviously from mechanical point of view, we will be in a better position as we move towards continuous fiber. It will increase the elastic modulus, it will increase the strength of the material, but at the same time at the cost of higher costs. Then based on that, what type of matrix, what type of reinforcement we are using, there are classifications for these composites. If we are going for the polymer based matrix, it is polymer composite, it may be metal, the matrix may be metal, matrix may be ceramic. Then reinforcement, it may be particulates, it may be fiber. Obviously, there are these extra fillers or coupling agents to improve the properties, to improve the weightability of the fibers or the reinforcements, to promote the formation of proper bond at the fiber matrix interface, and accordingly the design of the composite material takes place. Composites are typically differ from alloys in a sense that when we talk about alloys, they combine the different elements. Obviously, at least one of them generally is metal, and they combine
the slides are not moving.
Slides are not moving. Let me just check.
Yeah, I think you have taken it a full size in that mode. Yeah.
Now it's okay?
Yeah, yes, sir.
It's moving, no? Okay. So now if we talk about the advantages of the composites, obviously one of the major utility is in the form of your weight saving, because always when we talk about different components where we will be using the composites, the requirement is to high specific strength, that is your strength to density or strength to weight should be high, then modulus to density ratio. So that is one of the major advantage we want to get from composites. Then the other thing is that its durability, or how long it endure the environment. That means the corrosion resistance properties, high corrosion resistance. Then in different cases we look for the other properties like electrical insulation, then fabrication of different complex shapes with the use of low cost tooling, then integration of many components in a single composite part, even small productions of objects with complex shapes. If we look at the low cost applications, then composites, they play a great role. And then from other point of view, say fatigue resistance and fracture behaviors, all those advantages we want to get from composites, but at the same time, that is by tailor-making the constitution of the composite using the proper reinforcing materials. Then is it that we always get advantages, we always get the merits of the composites at our disposal? It is not, obviously. There are some lacuna or limitations for the composites as well. In some of the cases, if we choose a particular reinforcement to include higher mechanical properties, obviously for that we have to go for high cost. So typically in some of the situations, the high cost of the raw materials that becomes a hindrance. Then the fabrication process and assembly. I will talk about a little bit about the fabrication of metal matrix composites, and then we will see that different these fabrication techniques involve different tooling situations, and as a result of that, it involves high cost instruments as well. Then in some of the cases, it will have low resistance to temperature and moisture, particularly when we talk about the other variants, polymer based composites. So typically the composites are weak in the out of plane direction. That means how the your reinforcements are laid. Based on that, whether the matrix carries the primary load or the reinforcements, based on that there will be weaker direction. So it will have your directional properties, and accordingly when we fabricate the component, so at the component level we need to look at those aspects in mind, because it's not isotropic material. Then composites are susceptible to impact damage, and there may be delamination, and particularly for laminated composites, this ply separation becomes a major problem. Then composites are more difficult to repair than metallic structures. That's obvious, because it is not a homogeneous material. So accordingly, if we want to repair the components, it becomes difficult. These are some of the applications of the composite: automotive application, wind turbine application, civil engineering, sports equipments. I think I can omit these discussions. This is now. I'll skip some of these slides. Coming to metal matrix composites, obviously the with respect to unreinforced composite, rather without having composite, the major weight saving due to higher strength to weight ratio, and then exceptional dimensional stability, particularly when we are talking about the metal matrix composites. The properties of metals are intact, as well as that matrix metal, along with that the reinforcing particles, their superior properties are inbuilt inside the material. Then higher elevated temperature stability, that means with the creep resistance essentially increases, significant improvement in fatigue characteristics as well. With respect to your polymer matrix composites, obviously since here in metal matrix composites we have the metal as the matrix, so it has got higher strength, higher stiffness. Then your surface temperature, we can go for higher values. Electrical conductivity will be good, thermal conductivity will be much improved, better transverse properties as well. Then they can be joined, and then radiations survivability with respect to your laser, UV radiation or nuclear radiation, and typically don't have any contamination effect. That means no outgassing or moisture absorption problems, unlike your polymer matrix composites. So that way metal matrix composites are beneficial in these cases. In case of metal matrix composites as well, we can go for your particle reinforcement, we can go very short fiber or whisker reinforcement, we can use continuous fibers, or even laminated sheets we can use. Now, regarding the fabrication process for the composites, obviously it can be differentiated into three major categories. One is the liquid phase processing, then the solid state processing, and two-phase processing. In liquid phase processing, typically the metal will be in molten state, and then we will add the reinforcement into it, and then we will go for casting. Then that casting, we can go for your star casting, maybe squeeze casting, where in case of star casting, we will be actually mixing the reinforcements inside the molten metal using mechanical vibration. Then squeeze casting, where the reinforcement are into the molten metal using pressure, or we can spray. We can have spray casting, reactive processing, then compo casting, electromagnetic star casting. These are some of the variants. In case of solid state processing, basically we will not take the metal into the liquid state. In the solid phase itself, we can have diffusion bonding, we can have sintering, mechanical alloying, or even your powder metalling, powder metallurgy route, or fixed star processing as well. That is one of the latest technology. Then the looking at the individual processes, like say in star casting, what typically is being done, we will be having the matrix metal, then in the furnace it will be taken into the molten state, and then the reinforcement phase or the reinforcement particles, they will be preheated with a suitable temperature zone, and then they will be mechanically added to this molten metal, and then using the proper die or sand cast or permanent mold casting, we will have the cast material for the metal matrix. Then the problem with that is that the reinforcements, they may not get properly distributed. That means there may be problem of this agglomeration. Okay, so for that, what can be done is to go for something called what is ultrasonic vibration. Typically, if the particle size of the reinforcements are low, and nowadays people are looking at higher mechanical properties by avoiding the defects in the reinforcements. So when you want to minimize the defects, one need to go for smaller particle size. Different people are venturing into the nanometric sizes of the reinforcements, and in those cases, one of the major hindrance is the agglomeration of the particles. So when you are mixing mechanically the reinforcements, the reinforcing particles, they can agglomerate and they can form clusters. So to avoid that, what can be done is to break those clusters and to distribute them evenly in the molten metal by using proper ultrasonic probe. And then if the distribution is there more or less homogeneously mixed, and then you pour it into the mold and get the cast material.
Sir, hello, sir.
Yes.
Sir, actually, I think slide is not changing, sir.
Just
Now it is changed, sir.
no. This is the. So when I am going to the full screen, you are not getting, no?
Sir,
Just there may be some issue with the. Let me just do with something else. Is it now visible?
no, sir. Sir, again, sir, you stop presenting, then again you sir, start sharing.
Yeah, that will be better, and maybe I need to share the holes of my, instead of a single window, if I share my whole desktop, it may be
Sir,
just a minute. Is my desktop is visible
sir, desktop is visible, sir.
now?
Now it is visible, sir. Now it is changing, sir.
Sometimes because of low bandwidth, these
Sir.
things get disturbed. I don't know. Earlier, actually, I was sharing it from a single window, and now I have shared from the whole desktop. Let me see if everything is working properly or not. Now you can see, no?
Sir,
Okay. So after this ultrasonic vibration, that I was talking about this de-agglomeration technique by the use of ultrasonic vibration. Actually, when the particles are of very minute size, of the range of, say, nanometric scale, when we are dealing with nanometric particles, then there will be formation of these clusters. Now we need to break those clusters to get it evenly distributed in the molten metal, and for that, actually, what we incorporate this ultrasonic vibration probe, and basically through the sonotrode, when we give that vibration into these clusters, they get dissociated and they becomes de-agglomerated. Now, moving to the technique, essentially what we are using here in my lab, that is the combination of this ultrasonic vibration and the semi-solid stirring. So basically the molten metal is there, then nanoparticles are added to it. So initially we will be using the conventional mechanical stirrer, and then we can incorporate separately the ultrasonic horn or the ultrasonic probe to actually de-agglomerate those clusters. And we have seen that by utilizing both these combination of the ultrasonic vibration and the mechanical stirring, we could have a good quality cast, good in the sense of evenly distributed nanoparticles. Then the other techniques, though I have not worked in that in my facility also, we don't have, but this is another technique where this disintegrated melt deposition is being carried out, where it follows the typical mechanical stirring method. Only thing is that the molten metal is poured under inert gas environment and under a superheated condition, and then it gets deposited on the metallic substrate. And while depositing on the substrate, it gets basically evenly cast. Then the yield filtration technique, where the base alloy as well as the reinforcements they get in the molten state, the infiltration of the molten alloy into the preheated preforms take place under pressure, and then that is held under pressure for quite some time to get it solidified, and then the normal ejection of the solidified composite casting is done. Then other techniques like Rio casting or Thixo casting. These are some of the techniques where basically semi-solid state processing through which the metal matrix composites can be fabricated. Then one of the advanced technique we are working a little bit in that zone as well through a Ministry of Steel project, the friction stir processing, where we incorporate with the help of the typical geometry tool, we can fabricate the metal matrix composites with the incorporation of particular elements into the matrix with the help of stirring and the frictional heat generation to our advantage. Then the other processes include, one of the prominent one is this powder metallurgy process, obviously, where the mixing is in the solid state itself, where the base powder and the reinforcement, they are mixed properly and then they are compacted, and under pressure the typical green mold parts are generated, and then usual sintering process will lead to the finished product. Then this is another technique, equal channel angular pressing. From different orientations we can apply pressure to the compacted combination, and then we can get the desired shape as well. Now moving to tribological study of the metal matrix composites, typically I get the material prepared and fabricated to definite shape, but I need to see really whether with that aim, whether I am able to have the requisite value of coefficient of friction, the requisite value of wear coefficient or not. Because unless, okay, mechanical properties are good, fine, it will be long lasting, all these things are okay. But if the major part of my input in the system gets lost in the form of friction and wear from the components, then that particular material is of no use. So when I fabricate any kind of material, then I need to study it. Apart from its mechanical properties, I need to study the tribological characteristics as well. So whether at a particular situation it will have the definite kind of low friction, low wear characteristics or not. If that is not, then I need to look into the constitution again, and maybe I need to fix up some other proportion of the different reinforcements so that I can have improved friction and wear. Now, as a case study, I will take up a few things, at least one aluminium based metal matrix composite and one magnesium based metal matrix composites, because among the different metal matrices, this aluminium is most prominent, aluminium and magnesium, because of their particularly low weight considerations. So the first case study I will be presenting is the aluminium TiB2 metal matrix composite. So typically what we did, we take the base matrix as your aluminium, and as reinforcement we took this aluminium TiB2. Then we go for fabrication of the composites and we characterize the composites, and then we try to study its tribological characteristics. And while doing the tribological studies, we try to evaluate the tribological properties, the friction and wear, under different conditions. Maybe in the case of your dry sliding, then lubricated sliding, under lubrication how it behaves. Then if we use it in, say, engine cylinder and other applications, then obviously it will be exposed to high temperatures. So under elevated temperature condition, how they are behaving, and then to identify the tribochemical reactions that occur at the surface during all these processes, we need to look at the your wear characteristics and wear regime maps, and then the surface characteristics. And we did some amount of corrosion tests as well to see whether the material is behaving properly against corrosive environment or not. Now, these are some of the experimental setups. This is in a multi-tribo tester, then the pin-on disk machines. This is the high temperature tribo tester, where we have the heating coil inside the tribo test chamber, and we can control the temperature over there. And this is the corrosion setup. Call me after 1 hour. Then the setups used for characterization, typically the mechanical hardness. We characterize then the microstructural characteristics to EDX and XRD. We need to find out that what are the during tribological testing on the surface, what are the different materials gets embedded. Now here we essentially do the study to decide on the reinforcement, exactly what property of the reinforcement we want, and accordingly we need to choose the reinforcing particle. Here on aluminium we are using TiB2 to improve the mechanical properties. Then when we improve the mechanical properties like strength and your elastic modulus, hardness, alongside comes in that it may not give proper tribological characteristics as well. So if I want the tribo properties to be in good regime so that it can be used for normal tribological applications, for that you need to lower down the friction values, you need to lower down the wear properties. So we incorporated some amount of graphite as well. So that type of study we carried out. And here this is the for fabrication of the aluminium TiB2 composite. What we did initially, we tried with simple star casting method. Then what we found that even the TiB2 particles were not in the nanometric zone. They were your micron size particles, but even there were little bit of agglomeration, so there it don't get evenly distributed. So we tried to modify the star cast method with the help of ultrasonic vibration assistance, and when we do that, we could achieve much more uniform distribution of the particles in the matrix. So this is regarding some of the results. So these are the microstructures for 1 weight % TiB2 reinforced aluminium matrix composite, and the other one is for 5.5 weight %, and this is micro hardness plot. So when we vary the TiB2 percentage, what we find that there is more or less uniform increase in micro hardness. So that is obvious, that is expected, because your TiB2 has got much harder, much high hardness compared to your aluminium. So when we incorporate higher amount of TiB2, we achieve much greater hardness. Now, when we look at the dry sliding tribo test, typically we did it on a pin-on disk machine under dry sliding condition. We vary loads, then the operating speeds, and for different weight percentage of TiB2. So now the wear properties, what we could find that when it is pure aluminium, obviously your wear depth is much higher for the same combination of load and speed and other parametric conditions. And when we increase the incorporation of TiB2 particles, we get reduced wear. So that is obvious, as from your Archer's postulates that when you have higher hardness, your wear must go down. Looking at the coefficient of friction, what we can see when we increase the TiB2 particles, the coefficient of friction also reduces. So accordingly, what we can find that if you go for higher incorporation of TiB2 in aluminum matrix, then we get both in terms of wear and friction, we are in a better position. But at the same time, it is better with respect to aluminum matrix only. Now, if we look at the absolute values, then the coefficient of friction, it is of the order of say 0.2 or 0.25, something like that. And where coefficient values are also not very low. So what one needs to do, one needs to improvise to incorporate some sort of self-lubricating particles in the matrix so that we can have much improved friction and wear values. Then this is lubricated condition tribological test. We expose the same composite materials against in the pin-on-disc tribo test, but the tribo tester was flooded with lubricants, different lubricants we used, say 20W, then your chain lube oil, rice bran oil. These are some of the green lubricants typically common in today's perspective. So we did the experiments with that, and what we find that the trend of variation of the friction and wear, it is similar to dry contact conditions, that when we increase that TiB2 percentage, we get reduced wear and reduced friction. But when we compare with dry cases, obviously with lubrication, these are the situations for dry condition sliding. But when we are using the lubricants, obviously that gets reduced to a greater extent, and that is typical of lubrication effect, because when you are providing a third body in between the two contacting surfaces, the third lubricating layer that actually acts as a hindrance to direct metal to metal contact, so there will not be much of your asperity, tip junction formation, adhesion, plowing, all these phenomena, they get hampered, and as a result of that, your coefficient of friction will be much low and your wear behavior will be much high. Then when we expose the same components to your high temperature tribo testing. Basically in high temperature tribo testing, what we are doing, both the pin and the disc, they are in a closed atmosphere where we have the induction coils, and through that induction coil heating, we are maintaining a temperature say up to 500 degrees centigrade we can move to. And we try to do the experiments, but what we find, because of the melting point of aluminium and its change in the material properties, the wear rate, you can see it has been plotted up to say 200 degrees centigrade only. So as we go on increasing the temperature, initially at say up to 100, 150, there is not much change, but when we go beyond that, there is a very faster deterioration. At some point of time, actually what happens, it sticks to the pin, the composite pin, it gets struck to the disc as well, means there will be a typical scissor type of phenomena. So beyond 200 degrees centigrade or so, such type of metal matrix aluminum based composites are not applicable. So that is one of the major observation we found, that we cannot go beyond this temperature. So we have to restrict, even if we want to use it for high temperature applications, we have to be below this 200 degree, or it is better if we can restrict ourselves below 150 degrees centigrade or so. Regarding coefficient of friction, what we could see that when we are at low temperature means nearer to the room temperature, say around 25, 24 or even 50 degrees centigrade, the coefficient of friction will be of the order of 0.15, 0.2 in that domain. But when we increase the temperature, say around 200 degrees centigrade, coefficient of friction increases to a great extent. And also there will be metallic transfer from the disc to the pin. That means there will be this interdiffusion of the different elements leading to increased adhesion. And as we could see the same from the wear debris analysis as well. So we did the debris analysis, and the index of the debris spectra, they show the presence of the counter disc material in the composite pin as well. Now we did some corrosion study as well, and from that study what we could see that the corrosion behavior of your higher percentage TiB2 incorporation is good enough to resist any corrosion attack from the atmosphere or the corrosive environment applications. Then we tried to incorporate the self-lubricating nanographite into this metal matrix composite, aluminum TiB2, and inside that we incorporate some amount of nanographite. Actually, we incorporate 28% and 48% nanographite in different TiB2 combinations. This is aluminum 2.5% TiB2 and 2% graphite, then 2.5 TiB2 4% graphite, 5.5% TiB2 2% graphite, and 5.5% TiB2 4% graphite. So when we incorporate that, then typically what we can see that so far as micro hardness is concerned, when we incorporate this is for the base alloy or the matrix, the aluminum Si5Cu3, the base metal, and then with that when we incorporate graphite, you can see when we increase the graphite percentage keeping TiB2 same, since graphite is soft, so essentially there is a tendency of decrease in the slight decrease in the value for your micro hardness, and that is true for 2.5% TiB2 and 5.5% TiB2 in both the cases. And accordingly, when we go for the tribological tests, we can see that if we talk about the wear behavior, then with incorporation of graphite, actually our coefficient of friction reduces to a great extent. Okay. Because this graphite has got self-lubrication property. So even if it is dry sliding, the graphite particles or the graphite flakes, they get laid on the surface, and because of that we will have self-lubrication action, and as a result of that we get a reduced coefficient of friction, and also there is improvement in the wear properties as well. This is for the aluminum TiB2 nanographite under lubricated conditions. The observations are more or less similar, that even if you are having nanographite, the self-lubricating particles inside the matrix, if you have extra lubrication from outside, obviously that essentially reduces your coefficient of friction and wear as well. And for high temperature applications also, we get the similar kind of trend as observed in case of without nanographite. বিকেলে চলে আসবেন। Next, moving to the corrosion behaviors, similar observations. So to conclude the nature of aluminum particles, basically the hardness of the base alloy gets typically enhanced when we incorporate the hard ceramic TiB2 particles. Then with the increase in amount of TiB2, your friction and wear both gets reduced, and obviously there will be parametric variation with respect to your load and sliding speed as well. But the cautionary point is that these composites, aluminum based composites, they cannot perform at more than 200-degree operating temperature, because your matrix softening occurs with the rise in temperature, and that gets nullified due to the formation of protective layer on the composite surface at high temperature. Then your corrosion of the composites is better at bare minimum amount of reinforcement, after which it gets deteriorated, and then if we incorporate the nanographite as your solid lubricant inside the composite, the tribological properties will be much improved, even with the less amount of TiB2. Because if I can increase the amount of reinforcement of TiB2, that obviously enhances my tribological behaviors, but the same I can get with the incorporation of solid lubricant particles like nanographite as well. But the effect of solid lubricant do not get hampered by operational temperature rise up to the withstanding temperature of 200 degrees centigrade or so. Next, I move to another case study, the tribological behavior of magnesium metal matrix composite, where we incorporate tungsten carbide nanoparticles. So the procedure of analysis remains more or less the same. We select the base matrix, that is your magnesium, then we, as reinforcement, we incorporate tungsten carbide, then we fabricate the nanocomposites in the conventional star cast coupled with ultrasonic vibration. Then we characterize the nanoparticles to see that whether all the particles have been mixed or homogeneously distributed and evenly distributed, and the bonding is proper or not. And then we go for different behavioral characteristics like microhardness test, nano indentation, tribological test, and corrosion test. In tribology, we did dry sliding, elevated temperature test, abrasive test, scratch test, and then we try to correlate these test results with the composition to find out that which one is best suited. Now, regarding the choice of the reinforcement here with magnesium, why we are going for this tungsten carbide. Typically, tungsten carbide has got very high modulus value, then high hardness, high melting temperature, good thermal conductivity, high wear resistance, and as such, it does not react with the molten metal, so there is no negative effect from its boundary as well. And on the other hand, we are using magnesium alloy, basically MG3Al1Zn, AZ31, because of its good castability, good formability, and then it is easily available in the market, and it shows good prospect as material at ambient temperature. And we tried to explore whether the same can be used as elevated temperature as well. So this is the fabrication unit where we basically fabricate this magnesium AZ31WC composite. Typically, we set the target temperature of furnace at 750 degrees centigrade, and then AZ ingots are placed in the crucible. Then in the inert gas atmosphere, we did the stirring at around, say, 600 RPM stirring speed for 6 to 8 minutes, and then we insert the ultrasonic vibration sonotrode, and then we incorporate the particles in the melt, and in the vacuum atmosphere, we actually cast the material. And then we did the conventional different tribological tests, dry sliding, then elevated temperature test, then scratch testing, then abrasive testing, and nano indentation and corrosion tests to characterize the material. Now here the point is when we incorporate tungsten carbide, here also we can see that the hardness of the composite increases uniformly, more or less linearly it goes on increasing, and we actually incorporated up to 28% of tungsten carbide, and accordingly we could find the improvement in properties. Then we did the dry sliding tests, and the essential point of dry sliding test is that normally the wear and coefficient of friction, these properties, they behave in the same manner as for the metals, but the quantum is lower, means wear is low, friction is also low for incorporation of your tungsten carbide. And as we go on increasing the amount of tungsten carbide in the base metal, we did the experiment for different combinations of load and speed to see its applicability in different tribo-test situations. These are some of the glimpses of the incorporation of the particles, whether really we are able to incorporate the particles or not, and then during application of load, whether the particles are coming out or they remain embedded, or is there any metallic transfer from the counterface, to judge all those. These are some of the glimpses. And then when we do the elevated temperature test, here what we could see, we can go up to say 250 degrees centigrade temperature, and as we go on increasing the temperature, we could see the wear rate goes on increasing, though the coefficient of friction decreases. So to improve the properties further, here also we tried to give some amount of self lubrication particles as well. Here these are the scanning tracks for your scratch tests. Here we did some amount of nanoindentation test, since we are incorporating these tungsten carbide nanoparticles. So we tried to observe what is its improvement in the nano hardness and elastic properties, and we could see that with incorporation of higher amount of tungsten carbide, we could reach double the elastic modulus or even more. That is just because this tungsten carbide is so hard. And then we did these values and coefficient of friction characterization under scratch testing, and what we could see that when we increase the weight percentage of tungsten carbide, we are in a better position with respect to wear volume or coefficient of friction as well. Here you can see regarding coefficient of friction, these are for different loads. Obviously at higher load we have got higher coefficient of friction, and the negative point is that when we increase the tungsten carbide, then the coefficient of friction goes on increasing, though it's slightly. So by increasing tungsten carbide percentage, I will be in a better position with respect to mechanical properties. But with respect to tribo properties, typically with respect to coefficient of friction, that becomes an hindrance, that coefficient of friction goes on increasing. So I need to do something in that respect. So for that, this is another test setup where we study the abrasive wear test with the different grid size of the abrasive paper to see that what is their impact. This is corrosion behavior study where we could see that with the incorporation of tungsten carbide, the material does not get deteriorated that much. That typically the mechanical properties improve, but at the cost of corrosive resistance reduction. But here what we could see, there is not that much of reduction in the corrosion properties. These are the glimpses of the corrosion products and corrosion surfaces. The corrosion studies here, we did it in NaCl brine solution. Then we tried to incorporate the graphite nanoparticles in the magnesium tungsten carbide composite, and here we have got 1% tungsten carbide and 1% graphite, and then we increase the graphite to 2%, and the observations are more or less similar to the aluminum cases, because since graphite is softer than your tungsten carbide. So when I increase the graphite percentage, typically the micro hardness value reduces to some extent. But because of that, obviously wear will increase a little bit, but from the friction point of view, I will be in a better position. What is visible over here, that earlier the coefficient of friction used to increase with the percentage of your tungsten carbide, but here what we can see, when I incorporate higher amount of nanographite in the system, my coefficient of friction reduces to some extent, so that I am having coefficient of friction below say 0.5, 0.3 in that zone. We did some amount of statistical analysis as well to identify that exactly what percentage of these reinforcements will lead to the proper value for this wear and friction characteristics. So for that, there are different approaches. One can go this response surface analysis, one can do the Taguchi optimization, one can, if both friction and wear need to be reduced, then one can go for the gray analysis and all this. So these are routine work, routine statistical procedures. Using that, one can surely optimize the behavioral pattern. So we also did that to find out that exactly which combination of these parametric values will lead to the typical zone where I need to operate this coefficient of friction or wear. In some of the cases, obviously, it is a multi-dimensional problem because so many factors we are having. You have the matrix, you have the reinforcement, then the percentage of reinforcement, then along with that, you have got these tribological parameters, say applied load, the speed at which it is operating, then the sliding distance, how long it is being operated, and then the environmental conditions, whether you are having dry sliding or lubrication or your abrasive or your corrosive environment. So all these factors gets coupled together. Obviously, it is not possible to have any study that will incorporate all these factors. So we tried to do some experimentation in a limited way to identify the zones of operation. So finally, what we come out of those is that in magnesium, when we increase the percentage of tungsten carbide, since tungsten carbide has got very high hardness, so even if we incorporate 1%, 2% of this tungsten carbide, the micro hardness value increases to a great extent. In fact, the addition of 2-8% of tungsten carbide improves the micro hardness value around 52% compared to your base alloy. Then the dry sliding test reveals the wear rate of the base alloy is notably higher compared to your tungsten carbide nanoparticles. So if we really need to reduce the tribological losses, surely there is no other way than to go for some particulate incorporations. Coefficient of composites decreases with the increase of load and speed, that is in line with your Archer's observations. Then nanocomposites, they yield excellent tribological properties at elevated temperature. In case of aluminium, it was 200 degrees centigrade. Here we could go up to 250 degrees centigrade. Nano hardness and elastic modulus of the nanocomposites, they are also significantly higher. If we are looking at some low load applications, then obviously we can, these properties they are of importance. Abrasive wear rate of the base alloy always higher than the fabricated nanocomposites, because when we incorporate the nanoparticles, they take up the major load, and as a result of that, your wear rate is much lower. And regarding the corrosion behavior, what we could find that when we increase the tungsten carbide percentage, there is degradation in the corrosion behavior. So in magnesium, ideally through these optimization studies, what we could, and also the confirmatory test, what we could observe that 0.5% of tungsten carbide is the most corrosion resistant material among the base alloy, as well as the other variants we have studied up to 2% weight, 2% of tungsten carbide incorporations. Then incorporation of 1% of graphite nanoparticles that enhance the microhardness, nanohardness, tribological characteristics, and corrosion resistance. So in essence, from this study, what we could see that in case of magnesium and nanoparticle of tungsten carbide incorporation, the best suitable combination is 0.5% of your tungsten carbide coupled with 1% of nanographite. If we prepare that composite in a favorable manner, that actually balances both your mechanical properties as well as tribological properties to a great extent. So with that, I wrap up my lecture, and I will now invite questions from the audience.
Participant, do you have any question? Please ask. Hello, dear participant, do you have any question?
You can ask, or you can put in the chat box as well.
Sir, namaste.
Namaste.
Sir, is there any, you can say that just I need one suggestion here, like your fiber plastic, right? That means the transparent fibers, what generally we are using in the certain vehicles also now. So is there any relation between this and the topic what you taught here, the same manufacturing process? Just like in a bulletproof in the bulletproof car, right? The glasses, that is, I'm thinking that is not be a glass, that may be certain fiber related composite glass might have.
Yeah. That is fiber reinforced composites,
Fiber
but that is not in the metal matrix domain. Okay.
So in the same way, the manufacturing process will be here, sir. Just you explain.
No, when it will be glass, it is typically brittle material.
Sure.
So in those cases, generally they don't go for this casting procedure for them. Okay. So it's a purely, when you talk about glass matrix composites, it's a typically different domain. Okay. Their manufacturing process and fabrication process are purely different.
Sir, in certain cases, I have seen in certain journals the experiment they have taken during that simulation process or through the prototype model also. Suppose certain glass fiber or certain thing they have taken and they just strike with a hard metal, right? Instead of giving a crack in a different manner, only a steep crack is coming.
Okay.
Steep crack is, sir, the reason behind it that I also want to find out.
No, that is the how the material will behave. No, see the basic behavior of in terms of your fracture and other behavior, that will be determined by the matrix. So the matrix material, the properties will be there, and regarding the strength properties and other determinable properties, that will be due to the reinforcement. So what sort of reinforcement you are providing, that is based on the requirement. Right. Now here the overall failure behavior, that will be due to the matrix only. So if your matrix is having a certain kind of nature, so that will follow.
Thank you so much, sir. Thank you.
Thank you.
Good afternoon, sir. Sao, sir, this side, Dr. Pankaj. I just want to know the coefficient of friction you are mentioning over there. So, where is it applicable of this type of property, and how can we have to control through a rule of mixture? Is it possible we have to control coefficient of friction through a rule of mixture, and how much reinforced and how much matrix? What's your view about it?
Typically, this friction, rather coefficient of friction, is not a material property, first of all. Okay, this rule of mixture is generally applicable in case of material properties, say your density, okay, your elastic modulus. Unfortunately, this wear and friction, these are material responses, not material properties. By material response and material property, what I mean to say is that say friction coefficient for a particular material, we cannot have any tabulated value in the textbook or in the code or elsewhere, just because of the fact that it depends on so many factors.
But is it a system-based property?
Yeah, it's a system response. So the idea is you have to prepare the material, you have to go for your testing, and you have to have a simulated test condition similar to the one where you will be applying it. And accordingly, you have to
is there any
generate
link
data.
how we can formulate this thing to a reinforcing media rule of mixture? Is it what you think?
I have not seen any literature in that direction. Maybe there may be some issues, but I have not seen that particularly coefficient of friction or wear behavior in that.
Because
anybody
as you
applied.
mentioned in your conclusion, like, there is a 1%, some percent deteriorate with the or improved.
Yeah. That is purely based on the test conditions. We did those tests. Okay, for defined combination of the composites we prepared, we subjected those materials for the specific test conditions, and then we find that these are the applicable zones. Say, for example, magnesium, when we incorporate tungsten carbide, we incorporate 0.25, 0.5 weight%, 1%, 1.5, 2% that way. And what we could find that if I go on increasing this tungsten carbide reinforcement, I am in a better position with respect to my hardness, with my respect to my elastic modulus and strength values and all this. But at the same time, beyond 0.5 weight% of tungsten carbide, when I go, what I find that there is deterioration in the corrosion properties. So for tribo corrosion situations, typically not that always the component will be exposed to a very clean atmosphere. It will be subject to different environmental conditions, starting from your lubricant.
Might be your surface morphology can also play important role.
Yeah. So that is what, that in every case it is that is why tribology is an interdisciplinary subject and it is not a deterministic science. Okay, difficult to predict exactly what will happen.
Okay.
Thank you, Dr. Pankaj. Now, I would like to thank Professor Prashant Sao, sir, for delivering this wonderful lecture. Thanks a lot for accepting our invitation and presiding the session and spotlighting on one of the most demanding area, that tribology, from your vast area of research. I think this lecture that delivered by you definitely boosts the participant in carrying out their research. Your lecture on manufacturing metal matrix composite and their tribological characterization must give a new idea to various researchers, and especially the case study that on aluminum-based composite with graphite and TiB2 insert and another one is for same based with magnesium and tungsten carbide. That is found more interesting one. And once again, I thank you for accepting our invitation and gracing the occasion. Thank you, sir.
Thank you all, and very good afternoon to everybody, and have a happy new year.
Sir,
Coming-
same to you, sir. Wish you a happy new year, sir.
Okay, thank you.
Thank you.
Good day.
Now, dear participant, again we'll meet at sharp 2:45 p.m. For our third